Welcome to the talk. The title of the talk is Did Turing Awards Go to Fraud? It is the episode number 6 of the BMTalk 3D. In the last episode, we talked about plagiarism of Turing Awards. At the beginning, we mentioned law and regulations, and let's review that. So this talk is exercising freedom of speech, and as a professor, I have also right of academic freedom, and there are laws that defining defamation. In order to prove defamation, there are very strict laws. One of the requirements is that you need to prove that what I stated is false. The second is that I must present it as a fact. At this point, I only present evidence, and I do not intend to conclude that everything I claim here as a fraud is a fact. If somebody reported to authorities like ACM, like universities, like employers, they are protected activities because it is up to the authority to make decision. The respondent should not and cannot retaliate. Let's look at the U.S. laws on fraud. Title 18 of U.S. Code on fraud by wire. Whoever having devised or intending to devise any scheme or artifice to defraud or for obtaining money or property by means of false or fraudulent pretenses, representations by means of wire or any writings for the purpose of executing such scheme or artifice shall be fined under this title or imprisoned not more than 20 years or both. Canadian laws on fraud states everyone who by deceit, falsehood, or other fraudulent means, whether or not it is a false pretense within the means of this act, defrauds the public or any person, whether ascertained or not, of any properties, money, or valuable securities, or any services. Let's look at the U.S. laws on negligence. U.S. tort laws 283. A failure to behave with the level of care that someone of ordinary prudence would have exercised under the same circumstances. The behavior usually consists of actions, but can also consist of omissions when there is some duty to act. Canadian laws on negligence. The Supreme Court of Canada defined negligence as conduct that creates an objectively unreasonable risk of harm. This can include intentional and unintentional actions or even lack of actions. Let's review well-documented approaches to pattern recognition. I will talk about 2 schools. The first school is Symbolic School. I quote here is the work by K. Sen Fu. The title is A Step Towards Unification of Syntactic and Statistical Pattern Recognition. The reason that I used Symbolic School is that there is always a model, then there are symbolic concept that's handcrafted statically in the method. For example, suppose you want to recognize handwritten E. The model will have edges and has certain lengths. There are connection relationship. That's typical. If those parameters have variations, then you have a statistical measurement of the parameters. Another school is called connectionist school, or neural networks approach. Here, I'd like to present Professor Kunihiko Fukushima's neocognition, and I cited this work earlier too in the last episode. This is the neural networks, and I will review the difference between the symbolic school and the connection school. So symbolic score versus connectionist score look at some major characteristics. And symbolic score is feature-centered process. It has discrete features. Case full situation, you have ages, you have angles, you have connections. Those are discrete features and symbolic concepts. In the neural network score, and typically use pixel-centered process. Basically, you compute based on receptors or pixels. Now you can see immediately the symbolic score will have a fewer computation because you need to identify features, and you don't spend a lot of effort on pixels that do not have features. But for a connectionist score, you need to compute at every pixel location. You tend to have more computations. But then a symbolic score, the processors are all different because you have different features, different parameters, and they are all different. But for neural networks, the process at each pixels tend to be uniform because they carry out basically the same operations. What the differences are typically are the weights of neurons. But the computation are uniform using those weights. The symbolic score, you need a model. In the full case, you have a model of letter E or other letters. You really need to know that model to start with. For 3D vision, and you require a 3D model. That's like aspect graph I talked about during the last episode. Over here, because you learn from the images, then typically a model is not required because in Fukushima's case, you just link the response to the symbolic label class at the end. Inside the network, you don't need a model. Symbolic score tend to be brittle because all the symbolic concepts are task rules specific for a task, and they are ad hoc for the task only. So if the representation is not sufficient, the system will break down very badly. And for connectionist schools, typically you have rules for the architectures. Same architecture tend to be able to deal with different inputs. So connectionist school, hopefully, is less brittle. So the rules are task-specific rules, handcrafted by human. And over here, task rules tend to be mostly emergent, although there are system parameters that are dependent on the task. I will talk about more next. Over here, can you deal with general scenes? It's almost hopeless, except for very limited cases like pattern recognition, like numerals, individual letters, and fingerprints. For general scenes, neural network has chances because computation is uniform and the rules are emergent. So you don't have to spend a lot of human labor to do task-specific rule creation and programming it. So this kind of a symbolic approach is harder to defraud. We need to tell what kind of rules are. The rules are specified very clearly. And in the connectionist approach, and the rules are emergent. So that many hidden phenomena, such as manipulation of the data, are not clearly specified, and the neural network tend to be a black box and can have cheating going on in the results. I will talk about next. Let's look at major difference Perceptron we talked during last episode and error backplot. Perceptron learning did not use error backplot. It's strictly frame-wise incremental learning across lifetime. It's learning incrementally and frame-wise incremental learning. And it's fully automatic inside network. Hebbian learning inside network, in other words, is unsupervised. It does not use class label to the last layer. Within each feature matching layer, we used nearest neighbor rule. The nearest neighbor rule is very robust in the sense that it does not have local minima, but does have a higher computational cost. Because we generate a feature as long as it's new. So you have many features generated, each feature corresponding to a neuronal plane. So there's free of local minima. That's why performance is very high. Use only one network. This is a developmental network because grows incrementally online. Is very different from error backprop, used many network and pick the luckiest one. And after Perceptron, many neural networks start use error backprop instead and face accused fraud that I will spend time mostly in this talk. Look at the early example, National Institute of Science Technology, NIST dataset for individual neural recognition handwritten. Training set is from US sensor workers, and that's one population, and the test set is from high school students. There are another population. So you can see that there are two different populations. So what I call it is writer independent, because trainers and the testers are disjoint. Don't have the same person in both training set and test set. And in speech recognition, for example, you like to have a speaker independent test so that you learn from some people and you recognize from another set of people. All right, they're called speaker independent. So originally, this data set supposed to be writer independent, but Gong reported that validation set using his network reached like 1% error, but if on the test set, it's much worse. He didn't specify how much worse. Probably not acceptable. You can see that from the human point of view, certain cases like that, right? If you are in the alphabet situation A to Z, then this probably look like W, but using human context, if it's a number, then this look like 4. You can see that human has a context. The CNN, convolutional neural network, does not use context. They tend to use just one shot, classify an individual letters or numerals from the image. Next, MNIST modified NIST dataset by Gong was such that he broke the test set into about 50% about 300K samples as training set, and about 50% of the 30K sample as test set. In other words, before it was meant to be writer independent, pattern recognition, MNIST data set is writer dependent because every writer must be in the training set and test set. In other words, it's an easier pattern recognition task with MNIST data set. Then he further add the left side into the training set, about 30K more from the original training set. But the first test set, he used only first 1,000 samples from the test set to test instead of 30K. So he used the 1,000 samples from the 30K only. That consists what we call MNIST data set. Look at the concept of split between training, validation, and test. Suppose I have a total amount of data available, and I split into training set and the test set. For disjoint test, non-training set contains the test set, and test set was not in the training set. So that's called disjoint test. For the substitution test, then the test set is within the training set. Because we want to use the training set to train the network so that it can be tested, so we further split the training set into training subset and validation subset. The training subset typically is larger because you need more data to train, and validation set is to verify whether the training network is good enough. The typical method for error backprop is the following. There are some variations, but if there is an honest one, that's typical. For each of 10,000 sets of architecture parameters, because you do not know how large of receptor field and how many features you need, and so on. So you need around, say, 10,000, could be much larger. Then for each of the set among 10,000, and you have to use random weights because error backprop start with random weights. For each of the 100 sets of random weights, why it's 100? Because the random planner is just shoot in the deck. So you need 100, and typically you can have more. Then go through the error backprop to get stuck into a local minimum using the training subset, using here. Got local minimum using error backprop. Then you pick up the best network among 100 using the validation set. So overall, how many network you have? You end up with 10,000. You have 10,000 network. Then you pick up the luckiest network among the 10,000 using the test set over here. Bottom line is that you have random weights, 100, for each of the architecture parameters. So totally, how many random network you have tried? You have tried 10,000 multiplied by 100. That's 1 million. That's example that you tried 1 million random networks. I talk about the major content of this talk. It's called fraud from post-selection. Suppose I have 1 million students, each corresponding local minima. Some did well, some did not so well, some did very badly. So we have 1 million students in Stanford University, hypothetically, all take the same ImageNet test. ImageNet is the context organized by Professor Li Feifei and others, with a single training validation test split. So we have a training validation test split. The backprop method will pick up the luckiest student having the best score in the test set. You pick the highest score student. I call it luckiest because it's random initial guess with the system parameters happens to be the best for test set. Then the post-selection method will report only the luckiest student as our Stanford University graduate and suddenly queued 999,999 students that was not picked up and not reporting them. So I call it post-selection. Why post-selection? Because after training, superficial training for 1 million students, and you will pick up the student based on test set. So it's post-selection on the test set. I call it fraud. Why it's fraud? Because you use the test set like training set because you want to select which student you want to report. So select student to report is part of training process. So look at what the Professor Lacun did, and he is a creator harmonist, and he had many entries. Those are the error rate. Those are the publications. There are many versions over the years, and the last one was from Schmidt-Huber and his student. I reached 0.23 for 1,000 samples. This is the 23 errors. That's based on post-selection. Why? Because the test set is available. All the neural networks they used started with random weights and a particular set of architectural parameters like receptive fields, like how many layers, and then you select the luckiest one, called post-selection. But David Kuster, a postdoc of Professor Chris Adami at MSU Beacon Center, funded by NSF, used genetic algorithms. He got 7 errors. So it's during the 2013 to 2014, and he got only 7 errors for the MNIST data set using genetic algorithms, and the error is about only a third of the 23 of the previous one, so-called best. Then David invited me to his seminar along with many others because he was excited. I quietly talked to him right after the seminar. I said that it doesn't count because you use the test set like a training set. let's call it post-selection. At that time, didn't call it post-selection. Then David Kushner, he immediately agreed. He understood what he did. And he also reported to Chris Adami about what I said. And later on, Chris said that I will understand the issue and it's not that simple. That's his comment. I will not get surprised if somebody got zero error on this data set, because more free parameters a system have, because genetic algorithm will have many free parameters, many. And the more chance for it to reach a lower error rate on the MNIST data set, as long as he uses post-selection on many networks. So the more freedom the network has, the more you try, the luckier you become to pick the best one, because you picked the best one based on the test set. But then do you think this test set can do well for the new data set? For example, do you think can do well around 30,000? Of course not. You understand? It's just overfitting of the data. It does not have a power of generalization, because neural network does not have high-level rules like the rules Symbolic school to handcrafted. All the CNN we know have no high-level rules at all, basically doing data fitting. You people think about it, hey, you talk about split, and we heard of something called cross-validation. So look at what the cross-validation is for. So MNIST data set, as it organized by Professor Lacombe, missed cross-validation. It should not do that. The reason cross-validation needed, because when you split the training set into training set and validation set, there is bias. You can make it such a way so that the result come out easier. So this is called cross-validation. This scheme is well recognized in pattern recognition and also in statistics. Divide the training set into 5 folds, equal size, 5 shares of equal size. Then you do 5 tests, and each test will have a system learned. First test, use the fold 1 for validation. Test 2, you use the fold 2 for validation. Third one, use fold 3 as a validation set. For the fourth experiment, you use fold 4, and the fifth experiment use fold 5 for validation set. So in other words, you end up with 5 systems. The green ones are used for training, blue ones are used for validation. So that somehow reduces the bias of splitting the training set and the validation set. Then after you are done, you use the 5 network, you test on the test set. Typically you do average. You find the average error of the 5 systems. So you do 5 experiments. Each experiment use different folds as a validation set. All 5 experiments are tested on the test set to get average error rate. However, cross-validation does not prevent post-selection. So in other words, Professor Lacombe can do better if he requests experiments to do cross-validation so that the error that you received will not be too biased. But even if he did cross-validation, that does not prevent the fraud I talk about next. So let's look into what do you mean by fraud. Because neural networks is a very challenging problem for highly complex tasks. Look at this situation. How do brains work? And I'll give you a global view what a network is doing to simulate the brain. Suppose I have a motor neurons, bird, cat, dog. 3 classes only, to be simple. Then I have a new view of a dog coming in, and I have trained the system with different inputs. Those are the birds, those are the cats, those are the dogs. Suppose I don't have many samples to learn from, and each sample can assign a new neuron. And that particular neuron will use that one as a weight and this neuron will use that one as a weight, and this one uses that as a weight, and so on. If I have a new input coming in, if this is close to that one, and suppose I have a competition. Now, this is very important. Suppose I have with competition, then the best match, the neuron, will be that one, right? Because it's has similar to that one and that win. And if you top one competition and only this one wins, and then just link that one to this. So you can just link one. But suppose I have a dog. Dog has a 4 kind of views. Then you have 4 neurons. The probability can be learned by the connection. So like 0.3, 0.2, 0.2, 0.3, add together 1. So we have a method in developmental network, DM, that incrementally learn the probability based on that if post-synaptic neuron fire, and what's probability for this neuron to fire. This is like 30% of chance. This is like 20% of chance. Incrementally learn that probability. Same thing for other class like bird. Those are the probability for each neuron to fire when the bird fires. Cat for same thing, and condition on the cat neurons fire. You supervise the output neuron to fire during the learning so that the probability can be computed. That's the end idea. There is also probability model for the matching from this one to this neuron. And this is also based on the clustering, unsupervised clustering or supervised. I will not talk about too much supervised in this talk because I want to discuss the flawed. And there is distribution of the weights here in high dimensional space, and you form clusters. Within the clusters, using that neuron as a representative. Suppose I don't have enough neurons, and I have 12 samples, but I have only 6 neurons. Then what do you do? Once you get in, I will find the nearest neighbor from this one. This one has first neuron, second neuron, so I have 6 neurons. In the first 6 sample comes in, that's this 6 neuron already assigned the weights. And no matter what kind of random weights they have, you pick the best match, you pick the winner, then the learning rate will be 1, and the retention rate will be 0, and the input will be immediately copied to the weight that one. So in other words, regardless of random weights, the resulting neural network for DM is exactly the same. I repeat again, regardless of the random weights, if you have a same sequence of learning, you get exactly DM, because the random weights only change which neuron to win, but will not change the result of random neuron. And over here that because you don't have enough neurons to as a representative, then I have those voters, and those voters will find the nearest neighbors, and once it's fired as a top 1 competition, this neuron will use this one as input to update its weights. So in other words, every representative in the government, like a committee, right? In the government will update its weights to better represent its constituents. Over here, 1, 2, 3, 4. All right, this one will have a weighted average of these images as its weight, and all done incrementally. But here, which is important, is that we have competition with a large number of neurons versus small number of neurons. This is very critical in terms of competition, and I talk about why competition is essential in the brain. Brain has inhibition between neurons, and each neuron have a team of competitors compete so that you have a fewer neurons to win. You start having, over here you have a top 1, but you can have a top K, I will talk about next. So competition is essential to automatically develop internal representations. Suppose I don't have competition. So here I can compare the way of competition you don't. And I use a well-known person in China called Mao Zedong. And many people in the US and developed country also know his name. He is like, I want more here. And this all connection here, this is like assigned jobs. You are supposed to help me. So I'm the Mao Zedong, I will ask you to help me. But there is another task too. And Mao Zedong did not know who should help this and who should pause this and who should pause this. He did not know. This is a huge problem. He thought he has a power. He wants to do job assignment. In other words, he wants to perform human resource assignment. But he did not have enough knowledge. So the problem is a mess. So Mao said, Mao, connected the neuron will say, yes, Mao. There will be huge problem. Suppose you are doing a back plug, because back plug is like back box. Then you have random weights. It's like you are like Mao Zedong, but use a random weights. Random weights, if you connect it with certain value, the larger the value, the more assignment. So the random weights, they are not connected, those are randomly connected. So this guy said more because input is dark, and input dark, you should make it, I want more. And all the neurons say, yes, I will help you. But you can see that these two neurons are connected to another dark view. Some are connected to other classes. You should not ask him, give example, this one, right? This one handled birds. And if this one help you, you really screwed up. You really screwed up what they should do. You just have a top-down command using random weights, and you screwed up many neurons. How can this kind of a network can perform well? No way. Somebody will talk to me saying, I use only one set of random weights, and ask him to give me the result. He has not got back to me yet. And from this picture, it's impossible to have a single random weights who can do well, because you do not know how to assign the resource. You don't know which one is for what. From top level, you don't. The whole thing here is a black box. So there are two ways of doing fraud I will talk about. The first one is human vision. Human will be a central planner. Another is doing post-selection to pick the luckiest one from a lucky random way. It's like I'm doing economy planning. I try many plans and pick the one that luckiest. So Hinton has an example. I quote the Hinton network. They said 60 million parameters and 650k neurons. That's 650 neurons. I looked all the ways together, 60 million parameters in each network. They rely on random planner. It's like random planner for the resource allocation and post-selection. I'll talk about post-selection next. So random planner versus computation-based free economy. So from the previous diagram, you can see that the issue is really the planning. Error backplot uses random planner. The DN uses computation-based economy. Why? Because competition top K and look at who is the winner. And you ask the best guy to perform and to modify because that's his job. Here, you try random planner. So in our example, you have 3 motor neurons, bird, cat, dog. They all want the resource. A 3 motor neuron need presynaptic neuron to assign to them to process a particular class. The weights from the feature layers to them is like a global resource allocation in an unknown but highly complex economy. It's like you have a highly complex economy going on. In error backplot, this resource assignment is random. You assign random weights for here and here. Random. And this is like economic planner that is random. I call it random planner. That is why error backpropagation must try many random ways so that slim hope will come up among many other bad random planners. In contrast, a DN, all previous neurons compete for goodness match in the current input dark image because neurons compete. who is the best, and I will be the best, not the others. Only key percentage of top winner neurons are allowed to fire and modify their weights, where K is small so that K winners are true experts. Particular example we had before, K could win, but for a real situation, we like to have a K to be larger than 1. Namely, there is like competition-based economy without any central controller, no planner at all. It's like a free economy. Free economy is a market-based competition. Globally, the free economy-based resource assignment will decide who are the winners. So let's look at once somebody was decided to be the winner, what it should do. It's a deeper understanding of the issue. Direction of improvement and step length. Suppose I have a neuron, and the neuron have 5 inputs. X1, 2, 3, 4, 5 are the inputs, and W1, 2, 3, 4, 5 are the weights. The X vector need to match the weights. And a gradient descent of a pre-synaptic neuron gives direction. If you compute, take a partial derivative, you see the gradient is this input. This is the gradient vector. You need to change the weight vector, all right, change this one. So how to change this one? You want to add a constant multiply by this vector to add back into the old value of W's. The error backpropagation will update all the synaptic neurons, messing up their roles because we don't know what each neuron is doing, basically what's connected to help me. So you screwed up. And further, it does not give the step length, the constant multiply, because you do not know how long the step should be. They use local method, like Newton method, and you don't know. So you use other ad hoc technique like momentum. In contrast, a DN is based on maximum likelihood. Gradient direction only compute the top K winners. It turns out to be maximum likelihood, so still use that direction as the increment. But maximum likelihood also give you step length, learning rate is step length. There is a retention rate, and the learning rate and retention rate equal to 1, so that retention rate is determined immediately after you get learning rate for every time t. So in other words, DN will update the weights of the winners, and their step size and direction are all optimal in the condition of incremental learning. And all other losers do not update their weights. So all random initial weights will result in the same DN network. Listen, very important. Although we start with random initial weights, but they result in the same network. Why? Because the first example of the update will forget all the random weights, because retention rate is 0. Once you have 1 here, retention is 0. So 0 multiply the random weights, you get 0 vector. Then this is 1 over 1 for time equal to 1. Your learning rate is 1. So the input weight will immediately copy into the weights of the winning neuron. Then the random weights only determine which neuron to win. But regardless which neuron to win, the result is still the same. And that's true for every initialization of neurons. So that's why at the end does not need to even try any second network. No need. From the discussion we had earlier, we can see many neural networks are in crisis. And let's talk about 2 major flaws. One is the open skull that allow humans to supervise or pick up hidden neurons. Fukushima's neoconnectron for fixed connection parts, and also for detection parts, also which part is picked up. Apollo's HMAX, Li-Fei's neural networks, long short-time memory, LSTM, and SOM for early work of SOM. For the selection on many random neural networks based on labeled test set, We have CNNs of hidden, Lacom, Banjo, and Alphabet, produce HMAX, leaf-face networks. Then we also LSTM, SOM, and more. I like to mention without the names. Reviewing an article for Frontiers of Neurorobotics. There is a paper on the grounding of language using robots. The team is from University of Hamburg in Germany and Tsinghua University in China. They claim the post-selection was only based on one single network. But from our discussion earlier, if you have only one network, how can you be so lucky that the allocation of resource for all the neurons was reasonable before you start to do local minima? You have only one random weight here and here. How can the resource allocation work well? No way. It's like a mess. Like Mao Zedong is doing economy. See two examples how to avoid both. So skull closed and use only one network. The Perceptron is skull closed and everything inside automatic and use only one network, but it's not optimal. But developmental network DM is also skull closed and only use one network, but it's also optimal in the sense of maximum likelihood. There are many papers about the local view, right? So local arguments about error backplot, and they all miss the random planar global view that I presented to you here. So the random planar view here is the first mathematically based global argument for error backplot, along with other network. All local arguments for error backpropagation have missed this global view. For example, Banjos, he has a paper about local behavior of his network, so claim void saddle point, but totally miss the entire loop picture of error backprop network that he was using. It's a local view and it's misleading. Now let's go back to how brain deal with a local minima. The skull is closed. In 2001, we already proposed autonomous development in science. A developmental method should not leave any child behind. You tried a network, and that network must successfully develop. So in other words, you start with network, then give it birth, then you can have many teachers coming in, and you interactively learn. Suppose I have 1 million DNA networks, or they are learners, each live in a different life. Why it's different life? Because every network have a different environment. I'll talk about a little more next. Each learner learn and test on the fly. Throughout the lifetime, you have young, older, and adult. Mathematics has proved for DN that every DN learner is optimal in the sense of maximum likelihood. Look at this situation. We tried many error back networks initialized by random weights and system parameters. And we have an optimal DM. Those are the early review of each epoch corresponding to the training set once, twice, second time. And you can see that over 10, our network, green one, the single DNA is always optimal in the master design. It's already reached that optimality in the first epoch. And even you reviewed it, did not really improve because it did not add any new information. And it's already optimal. Over here, that's the error backplot. 60% versus 70% error compared to a little over 20%. And if you do more, 100, 200, 300, 400, 500, and gradually go down because that luckiest assignment of the weights for job assignment, resource assignment, you really need to help, ask them to improve, even support the plan is good. All right, the data static example. You can see that there's no way to match our method. Test on the first there. not so late. So you can see that error backup is competition of the resource. I get to that later on. It's not really competing for techniques or concept. So why the DN, every DN normal brain is optimal? Suppose that DN is an acceptable model of the brain. Suppose we agree that DN is a valid approximation of all normal human brain. Because every model of biology is approximation, and biology has a lot of details. And DN optimal property means that each brain is optimal, conditioned on 1. The number of neurons, 2. Must use incremental learning, 3. The learning experience. Then, why some student got a straight 4.0 in MSU GPA is always straight 4.0. Some others dropped out of MSU, right? You are saying they have optimal brain. So I explained it. One of the reasons is that 3 is different for different students. So suppose we have twin boys that fight for a toy. Even their genes are the same. They're in the same room. They fight for the same toy. And the loser will get loser mentality. It's like unstable system. You always have a loser and a winner. And the loser will get a loser mentality. So even the twin boy, they will not have the same environment after this experience. So the learning experience is different. And there is also difference, give example, that family environments. All right, some parents are much more education aware and motivated students or their kids much better. And difference in which country you're born in. So a student born in China and a student born in the United States, and they are different. Laws are different. And different in social expectations. Give example, a lady and a man, society will have different expectations. That expectation will have impact on the environment, all right, the learning experience. So let's apply our understanding of the issue of self-organization, emergence of internal representation to existing where no work. The first I'd like to mention is Professor Kunihiro Fukushima near connectionist, and his paper is honest. He said that this is fixed. Basically, Professor Fukushima looked at the feature responses and use human vision, and he selects certain area, certain position that's more useful as a feature. Based on the test result, based on human vision, she used a human vision, that his vision, his understanding of the problem, and he also looked at the test result and picked the better features, so it's a post-selection. Professor Tommy Pardew, and they have HMAX, they also use human vision and post-selection. I outlined some of the key points they stated in the paper. Look at the example he said. He used sample to refer to the human post-selection. He said, we only sample the space of features and do not perform any clustering. So clustering is like automatic, right? You pick up cluster, but you do not have a freedom of select which cluster, how many cluster, right? And they use sample, so basically they humanly select features. And they use the post-selection, stated clustering in early version of their work lead to poor performance. So basically they finally decided automatic clustering is not something that they can get a better result, but instead they use a human vision. They did not deal with skill valuation either, and only limited number of locations because they hand-picked the locations and hand-picked the features from the network. And they did not even mention scale variations. Fei Li, her PhD thesis at Caltech, I mentioned some keywords like prior knowledge and cropped from the image rescaled to the size of 11 by 11. So in other words, she will not deal with scales, but rather from that scale, she handpicked using human vision, then cropped to 11:11. So that crop is using human vision. For example, she will look at the scale. Do we see that? The bigger ones, small ones. And she will use her hand-picked scale. That's I guess from what she wrote, because she never talked about scale. And clearly there are scales there. Did not mention scale, human perceived scale. Rely on human vision, widely so in her later papers. Many her papers published in journal and conference, and did not talk about scale at all. In general, convergence occur within 100 iteration. That's her PME paper, one-shot learning. And for human vision, detect location and scales. So what do you mean by iterations? And she did not even talk about the iteration. I don't think iteration on the scale. It's iteration for computing the best fit probability. That's my guess. But she did not talk about what the iteration is. And for 100 iterations is way too small for scale. Perceptron will scale from the 32 by 32 all the way to 512 by 512. And she didn't do that. She at least didn't talk about that. So she basically looked at the scale in her vision, and then it's called human-assisted vision. Then I talk about political movement. So why political movements? By definition, politics is the way that people living in groups make decisions. The particular example I talk about human groups that make decisions. Political movement in China, one example is Great Leap Forward, initiated by Mao Zedong. The paramount leader in China has all the power, government, party, and military that lead to power corruption in China. And we have political movement in AI. One example is the ImageNet competition initiated by Professor Li Feifei that lead to alleged flaws in AI and Turing Award 2018. And unfortunately, NSF funded ImageNet, but not our Brain Mind Institute. So I would ask you to think about Feifei Li's negligence in ImageNet context. So the test images was released as early as in July the 10th, 2012. Then the result is due over 2 months after. So during that over 2 months, the winner probably have the chance to label the test set. You say, John, don't make a claim without evidence. I will give you circumstantial evidence to see through why. I already have methodology evidence. Error back prop without post-selection will not do very well. Not a chance if you have understood the method. The second is that post-selection need ground truth. If you do not have a ground truth for the test set, you only label the validation set, there's no guarantee you can do very well, although still a post-selection. But post-selection on the test set, look at that. So why I say probably labeled test set? Consider the random planner explanation of a backplot. From hindsight, it seems the only way to beat other method, you really need to do labeling of test set. And I'll give you more evidence. And in Negligence from Professor Li Feifei, she did not specify, I did not find any, explicit rules that ban labeling test set. It's like you have a closed book exam, but you give away answers very early, over 2 months ago. In contrast, look at how DARPA program manager managed the project. DARPA managed the project test allow only less than 8 hours between providing test set and answer due time. Teams probably do not have so many manpower to label the test set. Not enough time. You probably will not have enough manpower. Now, I would like to provide additional evidence, and I suspect the winner team supervision seems to be less credible than the second team ISI. That's from Japan. And look at the 3 tasks. Task 1 for classification, you provide a class label. Task 2, you provide location of the detected object. Task 3, you have a fine-grained classification. So basically, you have a much fine-grained classification. In other words, you need to label the test set more classes. ISI is in task 3, probably did not label the test set because that's a lot of label. If you label the fine-grained many class label, many more than task 1 and 2. The supervision has about 15 and 60%, and the second one 26. That's about 10% difference, major difference. Then look at the task 3 from supervision. The team here, number 3 position, or second team after supervision, was in task 3, but then supervision is missing from task 3. It's not just missing from first place, they did not submit at all. Task 3, fine-grained classification, you need much more labor to label the test set. And if supervision did not label the test set, it should be confident for task 3 too, but they did not submit the task 3. Supervision team decided not to submit task 3. Why? Because in the team information and abstract, they did not mention task 3 at all. So I would suggest that we should look into this evidence, although it's not direct evidence. And I suspect the team supervision has labeled the test set. And look further about the paper they wrote about the contest. They used the fully connected networks. That's a lot of parameters. They claim that 15% error versus 26. 2017, Professor Li Feifei misled public by claiming, I quote, "Machine's progress has basically reached and sometimes surpassed human level." This video is on YouTube. Somehow the Turing Award 2018 went to Professor Jeffrey Hinton, Joshua Benjo, Ian Lacombe for deep learning revolution, concept engineering breakthroughs, developed conceptual foundations for the field, identified surprising phenomena through experiments. Jeffrey Hinton, Joshua Benjo, Ian Lacombe for conceptual engineering breakthroughs that have made deep neural networks a critical component of computing. So look back. Look at Professor Lacombe. They use post-selection in their early work for 2D recognition. They use backpropagation specifically designed for the test. And that's in NIPS 1989. And the same year in Neurocomputation Journal, they use error backpropagation and use a post-selection also for 2D numeral recognition isolated, in this case from the zip code. Many years after, 89 to 98, 9 years after, they had a paper in Proceeding IEEE. They also use error backpropagation and also use the post-selection. And I discussed this plagiarizing phenomena, compare this one to the previous one. Although all those work from Professor Lacombe are all doing individual 2D numeral recognition. In Nature has a review article called cite many papers, did not cite Perceptron. And there is a title Deep Learning, Backpropagation Algorithm Breakthroughs, but they did not talk about any fact about post-selection. A CVPR 2014, Li Feifei published with Google staffers. That paper also used post-selection. January the 24th, 2017, I contacted Feifei Li and her PhD advisors for academic discussion because I have a lot of questions and they did not respond. Did alphabet widely falsified also? In Science Nature were papers that apparently use post-selections. Min et al. In Nature 2015 had as many as 20 authors. Graves et al. In Nature 2016 had also 20 authors. Graves was one of the papers that mentioned selections, but was not very clear what kind of selections they were talking about. It was selection based on the test set. Maravik et al. In Science 2017 had 10 authors. Bikini et al. In Nature 2020 had 31 authors. So indeed, each paper requires many manpowers to tune the architectural parameters and try a huge number of sets of random weights using post-selection on the ground truths that are available to every project. AlphaGo, a program that competed with human master levels in Go games, the issue that we need to investigate whether humans assisted by computers versus a single human. Is that a fair game? Interestingly, December 4th, 2019, Alphabet co-founders Larry Page and Sergey Brin relinquished control of Alphabet 60 days after they received a report on Alphabet plagiarism and falsification. I'd like to raise open question for us to discuss. Should such celebrities' human vision and post-selection behavior be hidden and spread across our AI research communities? And should future authors for the future papers check two checkboxes, whether you have human vision involved? If yes, how much? What nature? And also, do you have post-selection for the test set you have during the paper submission process? Is it on paper check or online check? Is ACM that awarded Turing Award under conflict interest situation in investigating Turing Awards research misconduct because they already awarded, give honor to the researchers who are accused of misconduct? And if it's indeed a conflict interest situation, what should ACM correct? Are the employers of celebrities under conflict interest situation, like New York University, University of Toronto, and the University of Montreal, and Google? If it is indeed a conflict situation, what should they correct? How can our research community hold these authorities accountable in handling a fair investigation into research misconduct? Why has so much US dollars gone to research misconduct? The work I mentioned over here in US are all well funded by National Science Foundation and other government funding agencies. What can journals, conferences, societies, and universities do better in the future to enforce research and publication ethics their policy specified? Thank you very much. If you'd like to provide comments, please feel free to do so. And if you'd like to contact me privately, please feel free to do so. Thank you very much.